Okay. Okay, hi. My name is Igor. Goran asked me to tell you a few words about my experience with FPGAs. I will be talking about this Jellyfish OPP. I will tell you what it is now. No, not yet. So yeah, basically I'm an embedded engineer. I'm not an FPGA programmer, developer, whatever. I just recently started using it, so this will be like completely beginner level stuff which I'm explaining, but I had a need to do that, and so these are a few things that that I did. So basically, what is Jellyfish? Jellyfish OPP, Jellyfish Open Power Profiler, is a project I started a year and a half ago. It's many things. I basically have an issue where I cannot stop adding features, so I just cram everything inside. So it's something. It's a main feature. It's power profiler. So it's oriented towards like ultra low power IoT stuff, where like device is sleeping, consuming microamp, and then switches to send the power like few hundred switch to a few hundred milliamps.
You're making a shadow.
Switches, and that's like really huge dynamic range of current consumption. So you need the device. If you're developing this sort of device, you need to precisely measure that current consumption, optimize it, and stuff like that. So basically, this the idea is to have a power profiler. It also can serve as programmable power supply. It can serve as programmable load, and since those two are like combined, it's basically, it can also be used as a battery simulator. So you can simulate the battery, charge it, discharge it, record some existing battery, and simulate it at different, like you need to test how the device behaves when the battery is at 5%, and you need to do that reproducibly multiple times. What basically is, it's a programmable two-quadrant source measure unit, which is like the correct name for it. But yeah, it has it can measure current across 6 ranges, from like under a microamp to 3 amps is like top design value. High sampling rate. ADCs inside can sample it to 3 megasample per second, but the analog bandwidth of the measurement should be around 150 kilohertz. It has a bunch of other stuff: external digital inputs, analog input, onboard user interface, additional power supply for powering other stuff, and yeah, basically whatever I had an idea for, I just put it in, and it turned from like quite simple device, which was the idea, into something quite big. So there are some commercial devices that do that, but there are no open hardware solutions, and I had some ideas that I can improve some parts of the existing ones. So yeah, that's why I started with this. And yeah, there's a low-cost solution from Nordic, Power Profiler Kit 2. It's amazing. It's like a small device under 100 euros, and it's basically good enough for most things. So this, I always put this tweet from like a year or something ago. Like, I basically want to do just that, but slightly improve it. And when I started adding features, I ended up with like over 20 pages of schematic just to cover everything I wanted. So it's still in development. This is the first prototype of the device, and in the next couple of weeks I'm gonna order the next iteration with some fixes. So yeah, this is the device. Because this is the like FPGA Meetup, I will most switch to that part. But like, here's the architecture of the device. We have like main power input, which has like controllable DC-DC converter. Then there's a linear stage, which can be used to source the current and to sync the current. After that, we have the current sensing for measuring current, and the output. Current sensing has those different ranges which can switch in between, and like we have the MCU, main MCU, which controls the like USB interface and onboard UI, like display, and things. And because it's high sampling rate, I decided to add a small FPGA to handle that sampling part, so that MCU can handle the display, the communication, and stuff like that. And FPGA does the hard stuff. So FPGA is controlling the DAC for setting the output voltage. FPGA is controlling the range switching, and it can do range switching based on the currently measured current. It controls the ADCs and the additional digital and analog inputs. And the thing is, when I got the first prototype of the device, I just wanted, the next task was just to test each section before I start working on the the usable firmware to using it. I just need to test everything. So for this it was easy. It was easy to put something on a display, test the USB. But then I realized all of this stuff here, in order to just confirm it works, I basically need to do everything because everything goes through the FPGA, and I basically need to write the whole FPGA part to just test these things. And I'm a complete beginner with the FPGAs. And so that's when my journey with it started. Connection between the MCU and the FPGA is quad SPI, because I needed something that is fast enough to transfer all the data, because that's 2 or 3 mega samples. I have 4 channels and digital inputs. It needs to be something relatively fast, and quad SPI is a standard interface on STM devices. So there's the communication between FPGA and MCU, and the FPGA then controls everything else. So I basically represent in the FPGAs as an external memory where I write some command or read something to get the data. So since I was complete noob, I started like this. We have first step. I have an LED, I have an FPGA. First write a blink so I can confirm I can do at least something. After blink, I need to do some better blink, because I have one LED, I have a bunch of IOs, but I need a way to verify that when I get to a more complex part, I need to see if it works. So I need something that which can be easily used to detect if something is okay or not. So that's the better blink. Better blink is just a blink where I can send it a number, it will blink that a number of times, and then make a short pause, and then do it again. So that's basically to test if I can communicate with the FPGA. I send it some number, and then it blinks that number of times. Second step was QSPI-COM. It was my first real module in Verilog. I started with Verilog. I basically just get started with the FPGA book, and it gave me some overview, and started with Verilog. So yeah, how I did it, basically needed to program the MCU to send some command. The thing with quad SPI, it has chip select, it has a clock, and it has 8 data lines, and those 8 data lines are bidirectional. They're used both for sending and receiving data. So at some point they can switch from being
4.
What?
4 or 8?
8.
8.
It is dual bank. So
dual.
yeah. At some point it switches from input to output and switches to high impedance. So basically to record it, I had to use the oscilloscope to actually check signals to see where it's switching from to high impedance for input to output. And it's tiny thing on board, so it looked like this. I had to do it multiple times to get all 10 signals. We have BB3 here and Easy Studio on the display. And I used chip select as a reference to record 2x2 signals to have everything. When I recorded it, basically this was the next step. Just figure out what I know I'm sending a command, but I need to somehow make a state machine to represent it. This was my first real thing with the FPGAs. So yeah, that I got it, and it was I made it. I figured it out. I made my nice state machine, but like there's these things that bites all the beginners in FPGA. If we see here, like we have the FPGA, it has its own clock, and we have the QSPI, which has a clock from the other side, and that then clock domain crossing. Where I made a state machine, it works, I run it in a simulator, everything is perfect, everything works. I put it on the device and nothing happens. And yeah, it was a good thing, it was solvable with just simple two-step buffer, but like that's the first part of the problem. Second part is like this is where the inputs go from pins go to high impedance to switch from input to output. Next thing is like, yeah, we have that direction switching. So I just made it naively, just like now it's input, now it's high Z, and it in simulator it works, of course. But then I put it on device, it doesn't work. So because I had to use, this is ICE40 FPGA. Like I basically just found the cheapest one, which should be powerful enough for that. So I had to use this SBIO blocks for those buffered tri-state pins, which is another thing I learned. And yeah, from that initial, like just I made the SPI communication work. I started from that, and then because I'm like when I send the SPI command, then I send some command with some address, and based on that command I like have some DMAX which decides where that address should go. Will it switch the range? Will it set the DAC? Will it read something from the block RAM? And we have separate ADC control, which like just reads the data from ADC, puts it in the block RAM, and yeah, like from my initial better blink in through like it was like a month and a half from now. Now I have this is not complete yet. Some modules still are missing some important features, but I'm getting a hang of it. So like I'm working on it, and I see the light at the end of the tunnel. So basically, lessons learned from this my expedition into FPGAs, like clock domain crossing is a bitch, and the real device doesn't work like in the simulation, like, especially when using those ICE40 blocks, which I need to make models for simulation because they are not known to the iVerilog simulator. But if we put that all aside, like it's a really cool thing, and I looking forward to use it in other projects too. So yeah, this was just in short. If you want to know more about Jellyfish device, it's like hyperwish.com/jellyfish, and just I need to for the end like light, and I can turn on better blinky with like let's say number 4, and it will blink 4 times. So yeah, it also has some more functionality, but that's not easily shown without everything else. So it blinks. Thanks. So now we can go to someone who actually knows FPGA.
Ask you a question.
If you have any questions, like, do.
Or no.
Okay, it's not a question, but maybe a comment, because I was also using often a SPI interface to communicate between, I don't know, ESP32 MicroPython and some core inside. And what I found out by experience is best to do in the FPGA part to emulate some known, for example, SPI memory chip. So you can write the memory, you can read the memory, and probably receive some interrupt. This is not in the memory, but you can easily implement it. This I found out to be the simplest. because if I see some project which has its own commands to talk with the SPI, it just becomes complicated, because then you are required to have some kind of a soft core on the other end, which you don't want. So some kind of low-level SPI memory is just fine. You have address mapping, so you can write to some address, and on this address you have just decoder and
Yeah.
it's traditional.
Yeah, that's
way.
exactly what I got here. Like
Okay.
how command
Yeah.
address and like just
Yeah, that's it.
I went this way because I wanted to use like the standard HAL functions from the MCU. I didn't want to invent my own protocol. I just wanted to use
Oh,
something. So
yeah, then
Yeah.
it is. So I would say it counts, it blinks, perhaps,
Yeah.
perhaps it thinks.
yeah, and it's funny like this better blink is consuming more memory cells than my QSPI decoder. Like it's because of the delays, but yeah.
It must.
So thank you.